So I had the experiment at SAN, NA44. It's related to HBT, and I built many detectors. And after that, I joined WA98 and start working on plastic ball detector and the Phoenix time of flight, and to measure the phi meson or this corrective flow. And it was the beginning of this corrective flow study. And I joined the Phoenix at Brookhaven, and just the first beam, I need to move to Riken. So, and after that, I joined Riken, and this is main subject is beta decay. It's completely different subject, and also the mass measurement in these days, and those are related to astrophysical L process nucleosynthesis topics. And I got this workshop information, and I prepared some slides during my study last 3 days. And this is I'm going to talk about some idea. Maybe this is new approach, that is the usage of this directed spectator beams for next experiment, and it's also related to deformed beam. And maybe I'm wrong, and this is very, I have never talked about this heavy ion experiment or topics for last 20 years. Just once, maybe at JPAC. So I might be very wrong. So this workshop, this is intersection of nuclear structure and high energy experiment. How can I do this? Maybe okay. Anyway, so for low energy nuclear structure side, so the energy is like keV or MeV. The main observable is neutron or proton or sometimes gamma or beta decays. And high energy, it's more violent environment people are interested in, like MeV or GeV or TeV, and pion, kaon, or proton or phi meson or kiva or whatever. So the language or the interests are quite different, I would say. So what is the difference of interest for between low energy nuclear structure and high energy? So this is my point of view. So for low energy nuclear structure side, people are interested in spectators, let's say. So we use, for example, uranium beam on beryllium target or xenon beam and whatever the beam, heavy ion, impinged on beryllium target and to produce the radioactive isotope. So the purpose is to expand the nuclear charge. This is the just two. And for high energy physics, this is the main interest of regions. So the at Riken, for example, there is some ruthenium isotope produced. So Zhang Liu, he is talking about the ruthenium-96 stable isotope, stable nuclei. And this produced the isotope at Riken. For example, we have additional 28 neutrons added using the uranium fission. So this is the difference. And back to this high energy nuclear collision story. So this is the main interest is this high temperature matters. And for example, early universe, or this is the image of star collaborations events. Okay, the temperature is very high. And if we go to more high density regions, there's another subject which we are interested in now. This is high density matter, and that can be connected with neutron star inside. This is also related to this recent research topics. and the R process nuclear synthesis, because we have also neutron star merger events observed by gravitational wave and electromagnetic counterparts are also reported. So it's very interesting topics also for nuclear structure side. So this corrective flow and the heavy ion collision. So I take this picture from Daniel Bitz. So the image is that how, so, and also Ultra, he is the pioneer of this corrective flow story. So the idea is to make the asymmetric initial condition and see how it evolves. And it's also very sensitive to pressure in high density matter. And here the right figure. So this is I take from this person, and this is another axis he mentioned. This is how about neutron rich matter. Wait, maybe I need to
hold it down.
hold it.
Don't release. Okay, maybe.
Ah, yes, I found it. Okay. Yes. So.
Something tricky for this work.
Unless
Yeah,
you
you need to point it at the mouse and then drag it. Then it will stay centered.
Yeah. And when you push the button, it shows up in the middle where it used to be, no matter where you're pointing.
It took me 5 minutes.
And then
Okay. Yes. Okay. Thank you. So the idea is to see the behavior of high density nuclear matter, especially neutron rich matter or pure neutron rich matter, to discuss about the neutron star core. Okay. So intersection of nuclear structure and high energy nuclear collision. Again, back to these topics. So I think the keyword is deformed nuclei, and also in my talk, I want to emphasize this spectator is also very important in this content. So what is the next step strategy for future experiment? This is one of the topics for big LHC experiment, but also for us, this lower energy heavy ion collision communities. So, and also there's some discussion about the feedback of this heavy ion collision to, let's say, nuclear structure, how the nuclear shape looks like using the snapshot of heavy ion, which people are discussing here. It's very interesting topics also for me, and this is also required feedback from nuclear structure, how we are sure about the deformed nuclei, the shape, and it can be also very sensitive, sensitive for discussing the initial condition. So, so Catherine and other people discuss about this deformation in nuclear chart. And for example, this is for example, the case of Ruthenium-96 or Zirconium-96 or Argon-166, which I may mention after this. So I prepared this. So and this figure, bottom figure, it's for example, the mapping of fast excited states, which is very sensitive proof to confirm the magicity. Like if the excited energy is high, so it means it's difficult to excite because it's very stable. And so that's why we have higher energy excited states in this magic regions. And this region, it's deformed, so it's easy to excite it. And this region is also one of the subjects for nuclear structure side, how the shape are. And it's very difficult to understand for each cases. Okay. And for example, these regions, there are many isomers some of them, this is blue point is corresponding to short-lived isomer below 1 millisecond. And the red point isotopes, they have longer-lived isomer. So some of them, they have both. So it is also one of the questions for heavy ion physics communities. If we have isomer, what to do? And application to heavy ion collisions, one of the subjects is deformed nuclei. So I got this contact for this workshop, and I try to see what is the discussion before in heavy ion community. So this is some paper from Horst, Stecker, or Reiner's group. So they are discussing about polarized beam collision. So this is tip-on-tip collision or body-body collisions. And they also discuss about the difference of multiplicity depending on the collision shape, status. So the initial condition is very sensitive for observer. So one of the topics, if I understand correctly, so if we pick up high multiplicity events, then maybe it may provide, we can constrain the condition, what kind of collision at the beginning. Am I right?
But they talk about polarized, the heavy.
Yeah.
I mean, it's chemically polarized.
Yeah, but yeah, I think this is also another question which I want to discuss.
So it's not spin polarized.
Yeah, shape. And if I think more carefully, or probably you may think more in deeply. So this is some typical event, collision event. But the reality, I think it's many cases of collision type. For example, if this case, okay, there is also another freedom of beam axis, how it's off center, and okay, this also changes the initial condition region here. Or if it's opposite different way, this way. Maybe
That works too.
this way, at the side view, we have this round shape, and deformed collision area is somewhere here, and there's some funny overlap regions, and it's a question if I don't know, this looks rectangular, but are you sensitive to this V3 component for this?
Yeah, I mean, what you do is, of course, is average over all possible orientation.
Right.
So indeed, if you look the mid-central collision, I mean, this is not the central collision.
Not
if you go away from ultra-central, you will see that beta 2 contribute to width 3. It
Beta 2 contribute to beta.
to width 3.
Yeah.
So because of this, it's all statistical.
Yes.
So there is an enhancement. Yeah.
So in other words, if you select some LHC, a lot of particles, so one event, if you pick up some V3 enhanced event.
Yeah, so no, I mean, first you're seeing events in centrality. So
Yes,
average, you go away from central collision, you will have this enhancement on V3 because of the beta 2.
Beta 2.
You pin them in multiplicity, which is not necessarily centrality.
Yeah.
Yeah.
Yes, but I think there is this nice idea, which I think Giuliano first pointed out, that you can also have, you have two handles. One is the multiplicity, and there is another handle, which is the, so multiplicity tells you essentially how many nucleons participate.
Right.
And there is another handle, which is the mean transverse momentum, which tells you how big the interaction area is. And so his point was, for instance, was when you take very central collisions where the nuclei completely overlap, if you have, for instance, oblate nuclei, if they get a body-body collision, then the size is larger than a tip-tip collision, and it also gives you a larger size means lower mean transfer momentum. So it's not something that we can do. It's not as good as multiplicity selection in the sense that really when you select multiplicity, you really select how many nucleons participate to a very good approximation somehow. On the other hand, mean transfer momentum has larger, fluctuates more, but still but you can still get around by constructing correlations. One example was this rho V2 correlation between V2 squared and mean PT that was discussed in the first talk. And it's really it's the same physics. It's really how the shape is correlated with the size. So I think that's how to understand it. And I think so maybe we can do. I wasn't aware of what Jiang said, that when you change beta 2, you use CD3. I think you can probably build more, and I think it's also something we should think about how because there are many things we can measure many correlations. Of very high order correlations. They are easy to measure. We just have to think hard. What are the ones that we want?
Yeah, actually, having a random orientation make the problem simpler. Because if you simpler because everything is statistical. But if there's some, if you can. No, if you.
I'd rather know.
What I mean is the random orientation. Because if you suppose you can polarize, but which you can't. Suppose you can polarize it. The problem is that you don't have 100% polarization. But you have to consider all this resolution. Yeah, but if everything is totally random, you can use your statistical tool to see, right? It's actually in a sense, for multi-particle correlation, it's actually good. Because otherwise, event-shift engineering is not perfect, right? Yeah, I think this we really see it if you write a global model, you will see this enhancement. Yeah.
Yeah. So it means the initial condition it's changed quite differently.
Yeah, you do random Euler angle.
Okay. And how about this case? Spherical and deformed central collision.
So you're right. I mean, you will see more spectator, right?
Yeah, the spectator in one direction and another side, nothing, or suppressed. And in this case, for example, collider experiment, it's advanced because you can see both forward and backward spectator.
So we haven't talked much about colliding different species.
That's right.
Is that a useful thing?
I don't know.
Maybe something that they can do.
You can.
Oh, it's also feasible.
At the rig is possible, but not the Large Hadron Collider.
This whole thing's a pie in the sky thing anyway, so we should at least consider.
Yeah. I think if you have a large spherical system like lead, and you only vary the shape of the other
like a
one.
small deformed thing hitting the lead,
even
like maybe you could very well see its shape.
Yeah, I think the level of sensitivity might be different because you instead of changing two things, you're only changing one, right? If one guy is always spherical, the other one is you can choose the deformation. It might give you may have more sensitivity.
Yeah.
I kind of like that Giuliano convinced me that you have two identical deformed nuclei, and you look at central collisions, they completely overlap. So it's as if you were looking at one single nucleus because they completely overlap. But of course, it doesn't mean that it's probably harder to collide one deformed with one spherical, but I think we should also consider it.
Wasn't this in the first talk when we had the two ellipsoids and one was perpendicular to this other and had this shape overlap?
So I think that the Polish group, right? They proposed the way to use the spherical system to analyze the shape of a alpha cluster. Carbon 12 or oxygen, whatever. Where you have a small system colliding with a large system, then you can really image the shape of the small system. Because you also produce a lot of particles. That's why your resolution actually is pretty good.
Actually, what feasibility technically can't LHCb do it with the smog thing?
It could. But
They could be
then
asymmetric, because they can
then
put in
it's,
some target there, and then the beam would be something else.
at the,
Actually, target.
at the LHC, unless you install another source, they cannot do it in the collider mode. Yeah, you need to,
They put it in fixed target mode.
yeah, fix target mode. But the rig.
Like the
all
entire
this
collider has to be a different mode, is what you're saying? Is it a detector thing or a collider thing that you're talking about?
Colliders.
Ah.
The problem, there's a limitation in collider.
So then the other experiments couldn't do anything during the entire run?
Only the only the smoke, you put a target.
And then Atlas and
No.
CMS just would shut down?
Well, no, we can run, we can do lead collation, but the lead, they collide with xenon, for example. Xenon in the smoke.
But you can do collider at the same time as you fix
Yes,
target.
yes.
Ah, okay, then I didn't, yeah, so that's no problem, right?
No, but it's fixed target, means low energy,
Yeah, but it doesn't destroy the beam.
doesn't destroy. But right now, the limitation is that you can only use gas target, means there's a limited choices.
Are there interesting gases, or noble gases? that
Right
you
now,
formed?
mostly they're using noble gas.
Any of them you formed in interesting ways?
Yeah.
Yeah, there's a neon 20.
Okay, great.
Yeah, sure.
They can do that.
Yeah, so this is a collider case, and a fixed target case, we can identify the fragment if it's in the beam line.
Mhm.
So this is the advantage of fixed target, which we are thinking. So,
Is this what you also plan to do in your,
yes,
for
in
this kind
future,
of thing?
in future,
So you can measure the spectator, right?
yes.
Then you can also study the
Yes,
deformation.
I think if the, yes, and yes, that's right. So if you have some nice idea for energy parts, then it's also very
How,
nice.
how do you distinguish, can you go back, how do you distinguish between these configurations where it drills a hole right through the middle and some others where
Yeah, that's good question. So we have forward spectrometer. So in principle, any fragment or spectator, we can measure everything event by event in the map,
You measure all the spectator, even the highly
including
charged.
you.
So how would you tell the
Yeah, but
difference?
it's not clear to me that the number of spectators changes drastically by changing.
Number of
Yeah, if you have,
spectators.
he's asking if you have two cases where you have the same number of participants, the same number of spectators, but in one case, they're like at two different ends, in the other case, they're at one end.
No,
Can you tell the difference between them?
no, but in each event you can, but you can always tell statistically whether you're colliding a spherical with, right? I mean, you have to do it statistically. For example, I said there's some study by the Chinese group in the ruthenium zirconium collision, which have different deformation than look the spectator neutron multiplicity distribution.
How is it?
You will see, yeah, I mean, spectator neutron multiplicity distribution will look different.
Forward.
But I have no idea
Summing forward.
how does the spectators, I don't know anything about spectators, so how does it look like? So does it look like you have is it only like neutrons and protons, or you have bits of nucleus?
You can measure more than the spectator
Yes,
neutron,
more
everything.
Yes, we can see. For example, this can be oxygen or neon or whatever, we can identify.
So
And
you
then
That's the
what
component
does,
of-
okay, and if we do this at the LHC, well,
in the LHC, no, LHC, we can only capture the free neutron.
but do you know, like, what is the fraction that, at least,
It's
what,
small,
if you
small
know,
fraction.
if you know how, so, okay, so it's a 3 newtons, a small fraction, most of it is like, I'm always been curious,
Yeah.
like, if you collide like, 2 lead nuclei at, with a fixed impact parameter, what the spectators would look like, is it just like small nuclei?
Most of them goes probably is a light ion, light nuclei.
I see, I
If
see.
they are bended away. The free neutron, let's see, in the mid-central collision where you produce the most spectators, in the lead, you can see 40 neutrons maximum. 40 neutron means of
40?
yeah, out of like a 200, 400 nucleons, which mid-central means you're breathing and you evaporate some neutron off, it's a 20, That's like 10%.
Tony's question was slightly different. I mean, at LHC, you see you can only separate the neutrons from the beam and the charge fragments.
Yes.
Whereas here, I understand you can see the neutrons, the charge fragments,
Right.
and they
Yeah.
are
In
all
fixed
separated from the beam.
Ring, it's difficult to identify.
So only on one side, right?
But then you
One side, only one side, unfortunately.
20 on each side or 40 total?
42,
20%.
yes.
So
But the good thing is that in the ultra-central collation, where if you have a spherical system, you will not have any spectators. But if you have deformation, you will see there are some spectator neutrons.
From the
Yeah, from the surface, and actually there's enhancement on the neutron number if you have a deformed system in the ultra-central collation.
Yeah, I know the effect of it.
Yeah,
mm.
so they're probably more sensitive to neutron scan, for example.
What picture is
Ah,
that?
Well, no, I mean,
Just a-
these people
calculation.
proposed that as a
Yeah,
measure.
it's right, yes, yes. That's interesting. Okay, so this is now open question because it's informal meeting. So one question, so there was discussion about any possible isomer collision in week or we discussed on first day, Monday. So we check, what, is there any isomer in xenon? Yes, there is, actually. This is the 8.9 days of half-life. I took this figure from NTC, and anyway, it's a question how much isomer still remaining in the ring. And I first thought, okay, we have at the beginning no isomer, and after the Coulomb excitation, maybe the number of isomer may increase, but I don't know the duty cycle of LHC, maybe 20 seconds. I don't know. Anyway, so you said 2 hours for
The beam time, the
Yeah,
beam,
beam-
they last, no, like 5 hours. 6
5
hours.
hours, yeah. Okay, so but anyway, the time scale is longer, but this cross section we need to check how much we can produce. That was the conclusion, and probably it's very low fraction, very negligible. But if there is some sensitivity to find out some special collision, if it's quite a different shape, maybe it may be challenging, but it's maybe interesting.
So I think our discussion, the concern was that this might be a contamination, right?
Yeah, for your yes.
But
For
if the shape are the same, then it's okay, but
Yeah.
if the shape is different.
especially for finding some exotic events, maybe it's can.
It's maybe a dumb question, but so the amount of isomers increases with the beam time?
If it's yes.
If you keep like Coulomb excite them and then decay back.
That's another question, like, do they not have time to decay before?
I mean,
There's a probability of decay.
Lifetime is 9 days.
9 days.
Ah, for this one, okay.
Actually, the actual lifetime probably much longer because
Because of
this
Lorentz
last-
boost.
no, also that, but this half lifetime is because the decay is through the internal conversion with electron
This one,
or something like that.
this one is probably this spin issue. So that's
This is internal IT, right? IT is 100%. What is IT? IT is
internal transition.
You know
internal.
what is feeding of this isomer in theta decay that is from internal.
So
That is from the CDK.
this, what does IT?
I know, IT decay, yeah, that's true.
I mean, what does IT? Because I was,
Oh, but they say it's an
If you guys
M4.
don't know, oh,
They say it's an M4, it means it's gamma.
Yes, it's gamma. If it's E, then
what is IT?
gamma.
so internal transition. Just spin is so different, so it takes time to.
Okay, but so it's only the
In
nucleus,
this case, yes.
only the nucleus, this one's only nucleus, okay. But there's a lifetime boosted by
That's
factor
some
1 more than
internal conversion cases, not this case.
It just emits a gamma and goes down to the.
Hmm?
It just emits a gamma
Gamma.
and goes
Go
down.
down.
Yes.
and the 200 keV.
Yeah. So this energy is like 200 40 kV. It's small, but it's okay. Then I found some, maybe you might ask those people or battery in Darmstadt, they can calculate how much fraction of isotope can be cool inside this.
No,
This-
we cannot, this energy, we can.
Maybe too high.
No, we give it to.
Hey. Okay, this is how about Rick? So gold. So he discussed that okay, the half life is 7 seconds. There is some ice, and if we multiply Lorentz factor gamma 14 minutes, but it's also question. It's probably very negligible. But there's also a question, if we have some converter before the injection of xenon in LHC, and we can enhance, we have a lot of
I
material.
think we need to ask the mission people. Yeah, we don't know. We don't know the-
And just put,
Yeah, I'll send an email to,
just stupid idea, but maybe
but
you
I,
may see some difference in the collision. Okay, second open questions. So is there any possibility to control the form of the nuclei? So this is related to lower energy heavy ion collisions. So this is ligand facilities, for example, and we can accelerate the uranium up to 400, 345. Anyway, so one of the motivation which I pointed out, I want to point out, that is, for example, fragment. So in high energy physics field, it's spectator. So if we have peripheral collision, so we can introduce angular momentum relatively smaller. If it's mid-central, semi-central, then it enhances its angular momentum, and central collision it's decrease naturally because it's central collision. So it's a question related to this semi-central collision, for example. So for example, at the fixed target facility like GSI or RICAN, RIBF, for example, we can use uranium to make whatever those isotope freely. For example, this is the image, particle identification case for these regions. And we have cocktail beam, but we can have some systematic way of nucleus collision. And it also depends on how much rate we can achieve. This is another question, but high intensity beam facility, I think we can perform this kind of collision. And the next question is, we are now requesting red beam because we are more interested in neutron-rich high-density matter. But uranium case, we have fission, so it's difficult to, so we have a lot of fission product, and it's difficult to select some violent fragmentation reaction. So red beam is a very nice beam to select, and GSI can do it now. We have no red beam. So last year, one of the motivation for requesting red beam is part of this program. Oh, and
so the purpose is to produce deform the nuclei and then you measure their transitions. So.
Yes, there are many applications probably we can think about. One of the physics cases deform the nuclei and the spherical nuclei collision in this case.
So the radon 206.
Yes.
That's for the octuple or something like that.
Yeah, this is somewhere here.
Okay, that's it. Right, but is this?
We can select whatever the expected.
Yeah, you have them, right?
Yes. I think this one is, I think some, uranium is, so somewhere here.
Yeah. So you do produce them.
Yes. Or proton mixer ET to identify. So back to this story. So I call directed spectator beam because it's spectator. And the idea is, okay, we have heavy ion. First, we collide, make a collision. And let's say we have xenon and tungsten target to or whatever, and we make the spectator. This is the first step. And second step, okay, if we have the spectator and depends on energy, but there's some bounce off of this, the trajectory changed. And the idea is, okay, we have some possibility to have angular dispersion matching. So the related to beam, this is straight beam, and we have some sensitivity to angular. So the primary beam stops in this area, and this trajectory change from the beam axis can go through, and we can detect the position, and which is related to which way the spectator goes. This is very primitive idea, but if it works, it will be very interesting. And after that, we identify this spectator event by event. And first step, probably we put some reaction detector, plane detector here, so that we can confirm if it's what we expected, event by event.
This reaction plane detector means you measure the reaction plane, you measure the
reaction. This is particle emitted in target rapidity region, for example.
Right, but is this for multiplicity detector, or this is
No,
actually
no,
to measure the deflection?
Measure the direction, which way.
So you will know the V1 direction.
Right. That is the idea, and we have some pilot experiment at HIMAC, and it looks working. So, and third, we transport this beam to each experimental port, like Samurai or 0 degree, or there are many ports, and we can try to perform double differential refraction study or whatever, which can correlate it with this position here. Maybe I should. Yes. So this is summary. And of course, there is also some possibility of isomers. And for example, this is the case of GSI energy, and they have mass link ESR, and they can identify, oh, there is isomer in short time. Yeah. So what they do, they inject the produce the isotope in the ring, and they can see the isomer decaying to ground state in time.
Just for the laser.
Yeah, just for laser. This way to here as a function of time. This is 7 to 35 seconds. This is the case for GSI. And there's some discussion about, for example, nickel 68. So the shape of nickel 68, ground state or excited state, there is some theoretical prediction that the shape can be changed, or there is some different shape in same isotope. So if we have some capability to identify those isomer event by event using very good timing detector in the beamline, so there is some, this is very challenging, but there is some possibility to have the reaction plane or this flow analysis and combination of this isomer. But fixed target.
But what do you learn by knowing the, the reaction plane in the collision versus the deformation of the product? Like,
So the ground state, it should be spherical
Yeah.
for these cases. If it's deformed, then we have different emission of particle in the heavy ion collision. And event by event, we identify, okay, this is isomer. This is nuclear 68. And we know that the point is this energy and this energy is large enough so that we may be able to identify the high energy state of isomer.
what is colliding there? Like you have two circles.
For example, this one we can use krypton, which yes, krypton 86 fragmented, and we can make nickel 68 a lot. And using this reaction frame or this balance of information here and combination of this time of flight for isomer or ground state, we, in principle, if it's possible, we can see the quite different emission pattern in the heavy ion collision in downstream. This is some idea for application of this high energy reaction frame technique to low energy heavy ion collision. And third point, is there any common interest in high energy and low energy field? So this is one of the subjects which I'm interested in future. So that is high density nuclear matter, but I'm more interested in high density neutron rich nuclear matter, which I'm thinking that if we have very neutron rich isotope produced and make a collision and spectator, if it's proton side, then collision side area must be neutron enhanced collision matter, something like this. But it's also very challenging. So the background of this motivation, one of the cases is related to gravitational wave. So this paper is discussing about the gravitational wave frequency for different neutron star masses. And they expect some sensitivity of the high density matter if it's quark or hadron phase, how it's mixed. It was one of the discussion like what Hatsa-san or this Kojo-san are discussing these days related to this phenomena. And for example, heavy ion collision laboratory frame, the biggest interest area of density, like 3 times of normal nuclear density. These regions, there is some sensitive study for this phenomenon, especially I think flow analysis is very powerful to discuss this physics case. And this is what I said. Their group, they are also talking about this hadronic to quark phase. There is some transition and there is some difficulty to connect, and it's also very complicated according to them. And they expect the pressure gradient goes up at this nuclear density, and that's why this neutron star could not be crushed even twice of solar mass system. This is what they are saying, and we may be able to discuss related to this.
So for the equation state study, how the capability compared to what GSI can do?
GSI is probably best.
It's just because of the intensity.
Energy.
Oh, energy.
Energy. And RIBF, it's somewhere here. So it's just starting point where we see some difference.
So your energy, what's the energy range?
So this require density around 3 to 4 times of nuclear density,
Right.
which is corresponding to like Bravo frame for GB.
Okay, may I make a comment on this?
Yes. Betty.
This is Betty Sang from Michigan State University. So I want to say that yes, GSI has the advantage of getting higher energy, especially at fair. But GSI have no possibility. I wouldn't say no possibility, but GSI is not optimum in terms of using isotope beams. And if you're looking at neutron star, you want to look at the asymmetry part. And I would say Riken and also Avrip and hopefully we'll have Avrip 400 have that advantage that we are able to use a large range of isotope beams with different asymmetry than compared to GSI.
Thank you.
So you have the ability to
What I want to make a comment on is that the symmetry energy is not, the effect of symmetry energy decreases with energy because you get up in high temperature, the isotope, the asymmetry part is not that important. So that's why at GSI, when they have very high energy, then they are mainly interested in the, or mainly sensitive to the symmetric matter part, not the energy, which is very important for neutron star physics. Okay, sorry for interrupting.
Thank you very much for this.
You can ask questions. So for this, what's the energy range you can cover?
Yes. At Riken up to 300 MeV. Probably.
But here you said
This is the case of if we have JPEG or
in the future.
Future.
But you have the flexibility to have collide anything you want. So like any, so you can produce many different beams and collide different systems.
I think
You have
beam
better-
species we can make any kind of beam.
Any kind of beam.
Yes.
What about the intensity?
Intensity, it's high enough. It also depends on how far this primary beam relative to fragment are. So if it's very far, the production yield will be
Right.
So it also depends on how much this bounce over this reaction filter we want.
Right, there are two aspects. If you collide a stable, then stable species, that's okay, right?
Stable, it's easy.
Right, then you can collide radioactive,
Yes,
like
yes.
That's ions.
Yes.
Okay.
If you come to back, let's say, to this figure with neutron star, this is, let's say, look, what is happening in the center is very speculative. Let's say there, okay,
It's very
from
speculative.
high matter, quark gluon plasma, some even
Yes.
speak about dark
Yes.
matter. let's say.
Because high energy side, it's nice to have QGP inside neutron star. QGP, it's soft, probably when it may crash. So it's an open question about the neutron star inside. Yeah, I don't know what's going on for inside.
No, there is no consensus, let's say.
Consensus, yeah. So this is some example. So if people have opposite the different way of physics case or which can be approached experimentally, it's very nice. I mean, so different theoretical prediction is also very nice to compare which are correct. Anyway, so
We have time.
So in Japan, we have another facility, HIMAC, which is mainly used for medical purpose. So daytime people use heavy ion like carbon inject on body. So for carbon therapy. But at night, we have capability to use higher energy of, for example, xenon beam, like 400 MeV or 600 MeV, if we like. So this is another port. And so we had some test experiments to perform like how it works for collective flow at this energy. So this was already done at GSI, but we want to confirm the directed flow or electric flow. So it was very small experiment. So we had we have target here, and we have some particle identification capability plastic situation arrays with pulse-shaped discrimination capability. So we can identify ion or neutron or proton or whatever in this region, target rapidity regions, and mid rapidity region or forward rapidity. We have reaction plane detectors, and by the way, this PMD I take from NA44 H1 photoscope. More than 30 years old PMD, still working very well. And we can identify proton, neutron very fairly. This work we started working with Tsukuba Group, some collaborators. Maybe it's too early to show, so I skip. We discuss about, we try to see the, okay, maybe it's preliminary, so don't take it seriously. So we identify the reaction plane using forward detectors, and we know the resolution, reaction plane resolution, and try to see the V1 at target rapidity regions.
Which particles do you use? To
We
determine the
check
reaction rate?
proton and neutron at the same event, but we have capability to identify proton or neutron. And this is preliminary, so anyway, but the proton as a function of PT, this is P, but PT, and neutron, we start looking at the V1. And there is some background discussion with Bowen-Lee that there is some sensitivity of this equation state. If we measure neutron or proton, PT is also very important sometimes.
Since we have some time, so you detect the reaction plane with using, what did you say, protons and neutrons or both? Or?
Yes, reaction plane, we use charged particle, for example.
All of them.
Or yes, in principle. All.
Okay, and that gives you a plane, and then you
check.
define the V1 with respect to that.
Right. Right.
Okay.
And even by the
But there's autocorrelation, right?
What?
The same particle used for the reaction plane is also defining the V1. I mean,
no, this is
Not neutrons.
independent detectors and
different rapidity.
different rapidity.
Oh.
More of them are forward, and this is target rapidity.
Sorry, was this fixed?
It's
or-
almost a correlation.
So I see. So you measure the reaction plane from the
Right.
projectile, and then you look at the target region.
Yes, for the
For
yes,
the
that's right.
Okay.
So Tsukuba group check this reaction plane reaction for proton and neutron in near mid rapidity region. Anyway, the coverage is not so much.
How many events for that statistics?
This is
Probably you show the next slide.
this one.
How many collisions?
So trigger rate 200 hertz and over light times maybe two.
Too nice.
Too nice.
So, but you probably have excellent reaction plane resolution, right?
Accident.
It's excellent. You're very good. It's very high.
Yes.
Reaction plane resolution, I
Yes.
think,
So
in energy.
yeah, inside this region is very sensitive for this directed flow. It's the
It's a bounce
advantage.
off, right? It's a bounce off.
Yes.
Right?
But we measure not spectator, but we use spectator for centrality. But it's one of the examples for future. So this is maybe time is over. summary, so related to deformed nucleus sequence collisions, so what I said. So there are various type of collisions, which is open question for both high energy and low energy heavy ion collisions. And multiplicity PT or rapidity or whatever, this may make useful selection. And I think backward spectators are also very important, even for high energy heavy ion collisions. And okay, this V3 story, I don't know. The production of exotic nuclei is non-central collision. It is very useful for heavy ion collision in future, so that directed spectator beam using heavy ion collision in the beamline, which may provide new physics cases, such as like, for example, interaction cross-section measurement. They measure the integrated reaction rate to confirm the size of nuclei. But we have control of the deformation. Deformed nuclei, I think there is some capability to confirm the size or shape, or in addition to this interaction, the integrated reaction. And also this, I don't know, this is a proper word, but differential flow with bias or bounce of spectator collisions. I think it's a new idea, and in future, maybe this is very interesting topics if it works. And also isomers. And the third part, it's related to future plan for us, is high density nuclear matter. I think it's very exciting time for us also to discuss about this, for example, gravitational wave observation from neutron star merger or neutron star black hole merger, or whatever. I think in future this observation, of course, nuclear theory and experiment, it's very, we need a lot of interaction to discuss this kind of topics also. So this is all for my presentation.
Suppose you do let's say in this low energy reaction, okay? Mostly the spectators.
Spectator
Right,
is
right.
interest
Okay.
for fast space.
Right. Okay, but suppose you do the V1 measurement in the bounds of low energy region, and you perform this measurement using ASA bar. Suppose
Yes.
you do ruthenium zirconium. Suppose something,
Yeah.
this is not the optimal choice, but suppose you collide them, you can measure the V1.
Then
in these
we
two
may
systems.
see difference.
Do you see? Yeah. Do you maybe I don't know. The V1 signal so big,
Yes.
right? I mean, I don't know.
Probably
You
it's
will
also
see-
sensitive to centrality selection again.
No, but the centrality distribution also reflects the
Yes.
deformation. I mean, the central deformation, central distribution are sensitive as well as the V1 signal. You can make a ratio of the multiplicity distribution
Yeah.
itself, and then I don't know.
There is also one additional parameter that is this is spectator heavy ion collision, and we can also measure the spectator, second spectator, and see this neutron. So let's say we have the deformed nuclei,
Right.
and we don't know where the neutron or proton are. And if we make a collision, and we can also see the spectator component of neutron and proton. It may, yes, or as a spectator. So how much the probability of, if it's an equal neutron proton ratio, maybe it's alpha cluster or something like this. I don't know, this is feasible, but maybe someone may think about it. It's totally different approach.
Wait, I'm saying, we have like about some time left, so.
Any questions?
people should,
Any questions from virtual?
After
Certainly have time, but we don't have to take.
For the
Yeah,
for the
everyone
Jet
ready.
Park, the 40 what's the time scale for that upgrade to
I think I saw the slide. It's like more than 7 years later.
That's not that
It's
far. Never used that far.
It's not- but again, it's easy.
But so that's on the same time scale as the F-root. Sorry, the,
I
the,
think
for the
higher-
GSI.
Higher is faster.
They are faster.
Yeah, for higher.
Yeah, but they also got the military. I'm talking about the Germany,
Generally, I don't know. There is some delay
yeah,
because of.
GSI also.
So, like Betty said, maybe if you are, you can maybe fast. Okay.
Questions?
So I have one question.
Yes.
So for the sphere sound study.
Yeah.
It requires a large ground density and low temperature. Do you think?
Large multiplicity.
Yeah, large multiplicity, but large mu B or large ground density. And do you think the Rick energy?
Rick energy.
Yeah, at G wave in G wave.
You mean the best energy scan?
Yeah, and also the fixed target program can afford to.
Maybe, but it's also question. Yes, maybe, but I cannot answer because of how much you can go down.
3 GB, that's the
3 GB, 3 GB.
no, fixed target, 3
fixed
GB.
target.
Star data, a lot of data at 3 GB, but only for good one
That's
species.
nice.
Yeah,
Nice.
fixed target also have a energy scan. So
But they didn't collect many, just one species.
I see. It's nice to.
They took more than 1 billion, yeah, like more than 1 billion events.
Can you put some spectator detector on the?
No, I mean, only the ZDC. But I think, yeah,
It's
there's
for
not much,
neutral.
that's not much. I mean, actually, ZDC doesn't see anything because it's too far. They don't have the acceptance, yeah, because ZDC is 10 meters away and fixed target, there's no acceptance even for the neutrons. But the mid-orbit coverage is very good.
So if we have higher pressure, maybe enhance the flow.
No, you only see a very large signal.
But I have no idea what is the calibration of this.
But for your current energy, you are much lower. So
It's much, yes, it's